class. And what we're going to start today is chapter 2 in the notes, which is the section on determinants. And when we come back next week, we'll start speaking about some of the properties of the determinant. So the basic thing that we need to realize at the outset is that the determinant is simply going to be some sort of function which takes in a square matrix as an input and gives you just a real number as its output, right? And in many different ways you might define a function which takes in a square matrix and gives you a real number. You could, for example, just take a function which adds up every entry in the matrix, but that doesn't seem like it's going to be very useful. It's easy to do, but it's not very useful. You might also define a function where it takes in a square matrix and the output is just the top left entry, right? That would be very easy to calculate again, but it doesn't seem like it would be very useful. On the other hand, you might imagine a function which takes in a matrix, and if that matrix is invertible, it returns a value of 1, and if it's not invertible, it returns a value of 0, right? So that seems like a very useful function, but it's not clear how you would actually do that. The computation to check whether the matrix is invertible is quite difficult. You do some sort of Gauss production. So there's sort of two ways in which you can teach the determinant. And the way we're going to do this sort of backwards, because it's easier to do it backwards. The conceptually better way to do it, but it's quite difficult to do this, is to say that we like the determinant to be a function which has certain properties that are useful. And then you say, well, if it has these useful properties, what then should the determinant be? How can we calculate the determinant of a square matrix? And that turns out to be very difficult to do. So we're instead going to do it the other way around. We're going to say, this is how you calculate the determinant of a matrix, of a 2x2 matrix, or a 3x3, or a 4x4 matrix. And that calculation looks really odd. It's not clear why on earth we define the determinant in this particular way. But then what we'll do is we'll show that if you define the determinant using this very odd-looking calculation, it has some nice properties. So we're sort of working slightly backwards. Okay, so this is, let's say, the definition of the determinant. So the determinant is defined recursively. We'll start with the determinant just of a 2x2 matrix, and then we'll see bigger matrices, the determinants are calculated recursively in terms of smaller matrices. So the determinant A is, the notation we'll use is we'll write down F A, and we will sometimes also use this notation, just sort of absolute value of A. Although it's not an absolute value, it's a determinant. And we might write that like this, A, B, C, D. Right, so that's our matrix A, B, C, D. And the determinant we calculate the following way. We take this diagonal here, we multiply the two things on this diagonal, and we multiply the two things on that diagonal, and then we subtract them from each other. So you say AB, that's with a positive sign, and BC, the negative sign. The determinant of a 2x2 matrix A finds in this way. The determinant of 3x3 matrices or 4x3 is defined recursively. And I'm not going to jump in immediately with the recursive definition. It's sort of difficult to just understand the recursive definition. I'm rather going to work through an example, and we'll work through an example of a 3x3 matrix. I'll explain how you calculate the the determinant of a 3 by 3 matrix. And once we've done the 3 by 3 matrix, then we'll write down a sort of more formal, more rigorous recursive definition. So let's start with a 3 by 3 matrix. Start with a 3 by 3 matrix. Wait, sorry, not EG, X. That's what I'm using, for example. 3 by 3 matrix here. We're going to calculate the determinant. We'll just make up the matrix here. We'll go 1, 2, minus 1, 3, 1, 1, minus 2, 1. Okay. So I'm keeping all these numbers reasonably small, so hopefully our calculation isn't going to be too difficult. We're going to try to calculate the determinant of this 3 by 3 matrix. And the steps for calculating the determinant of a bigger matrix, something other than a 2 by 2 matrix on the form. The first thing you do, let's say step 1, is you pick a row or column, any row or column. If there's a row or a column which has zeros in it, choose that row or column. It'll make the calculations a little bit easier. So pick a row or column. Choose a row of column which has got a lot of zeros in it if you possibly can. In this case we can't. We know it is 0 element, so it doesn't matter which one we choose. 2. We introduce what is sort of a strange thing to understand. It's not clear why we do this. This is again sort of, like I said, going backwards. We're looking at this very strange computation rather than the properties, but we're going to introduce a sort of checkerboard pattern. Introduce this pattern of positive and negative sides of the matrix. So let's say, for the sake of argument, I'm just going to say, let's say we choose the first row, and then you introduce the checkerboard pattern, which is like this. You actually only need to introduce it in the first row. Maybe we should have introduced a checkerboard pattern, like so, of pluses and minuses. So the top left entry is always a positive, a plus, and the other entry is always minus. And now what we do is we expand along this row and we calculate a sum. Along the chosen row, calculating a sum of smaller determinants. So let me show you how you do this. So maybe let me call this matrix. That was the determinant B. So the determinant of B, you've chosen to expand along the first row. So you take a look at this first entry, and we see that there's a plus over there. So we write down plus 1. And we multiply this plus 1 by the determinant of a smaller matrix. And the determinant of a smaller matrix that we look at, we're looking at this plus 1. You pretend that this column and this row don't exist. So that would be 1, 1, 1, 3. 1, 1, 1, 3. Okay. So we've got this over here. So this had a minus, so we write down minus 2. And this will be multiplied by the determinant of a smaller matrix. And the smaller matrix that we look at, well, we pretend that this row and this column don't exist. So then it would be 3, 1, minus 2, 3. 3, 1, minus 2, 3. Like that. Have one more term. Okay, that's a 1 plus 1 plus 1. And now we take the determinant of the smaller matrix again. So we're going to ignore this row and we ignore that column. So it'll be 3, 1, minus 2, 1. Okay. And each of these smaller determinants now, we can evaluate using the rule that we have for the determinant of a 2 by 2 matrix. So this over here will be 3 times by 1 minus 1 times by minus 2. So that will be 3 plus 2. So this is going to be 5. And this is going to be 9 minus minus 2. So that will be 9 plus 2. This will be 11. And this will be 3 minus 1 is 2. Yes?
It's supposed to be a minus 1.
It's supposed to be a minus 1. Let me just check. Whoa, which one's supposed to be a minus 1? Oh, did I erase a minus over there? Okay, so that means that this should actually be a minus 1 here. Okay, did I erase it? Yeah, okay, sorry. I didn't mean to erase it. It's a 1, 2, minus 1. Yeah, that's the only place it will change. Okay, so let's write out our next row. So our next row is going to be 1 times by 3 minus 1, minus 2 times by 9 minus minus 2, minus 1 times by 3 minus 2. That will be 2, 9 plus 2 is 11, 11 times by minus 2 is minus 22, and minus 1 times by 5 is minus 5. So that will be minus 25. Okay, let me just zoom out. We can put the whole calculation on one page. Yes?
If you had chosen to start with a pattern with minus instead of plus, that means you get positive.
Yes, and you get positive 25, right? So it's important that you correctly put the pattern in, starting with the plus in the top left corner and sort of spreading out from there. Yes?
So this is the default method for matrices of the two.
Yeah. So the basic way we're going to do this is called the cofactor expansion, but we'll get into this in a moment.
There's a shortcut for 3 minus.
Are there shortcuts? I don't know. I mean, we see in general that we can use Gauss reduction to calculate determinants a little bit more quickly, but this is basically how you're going to do it. So what you might realize, if you just stop and think about this, particularly if you're doing computer engineering of some sort, is that this is computationally really difficult as the matrix gets bigger. You basically have a computation which has got n factorial. So you've got an n by n matrix, you've got n factorial computations that you need to do. So if you have a 3 by 3 matrix to calculate its determinant, you've got to calculate the determinants of 3 2 by 2 matrices. If you've got a 4 by 4 matrix, you need to calculate the determinant of 4 3 by 3 matrices. And each of those 3 by 3 matrices, you've got to calculate the determinant of 3 2 by 2 matrices. So you end up calculating 12 determinants. If you've got a 5 by 5 matrix, you've got to calculate 60 determinants. If you've got a 6 by 6 matrix, you've got to calculate 240 determinants. You end up doing lots of work very quickly, right? So actually calculating determinants using this method is only really feasible in the 3 by 3 case. For bigger cases, we'll see that there are some shortcuts that we can use that will help us do this. So I want to write up now the sort of formal definition a slightly more formal definition rather than just what is all this expansion and so on. So we need to just define a couple of terms. So we're going to define the minor. The minor Nij of an n by n matrix. And we've got Mij, we've got a minor that corresponds to every entry in that matrix. The minor Mij of an n by n matrix is the determinant of the n minus 1 by n minus 1 matrix formed by deleting row I and column J. Just take a look at this. Those smaller determinants that I wrote up over there, those would have been the minors. So that would have been M11, M12, and M13 that I've written up there. The minors are the names that we give to these smaller matrices. Yes? No, so the original matrix is n by n. So if we delete one row and one column, it'll be n minus 1, n minus 1. The cofactor is just the minor multiplied by this funny checkerboard minus 1 pattern. So the cofactor Cij is equal to minus 1 to the I plus j and ij. Minus 1 to the I plus j and mij. You should be able to convince yourselves pretty easily that this over here is responsible for that plus minus plus minus plus minus pattern that covers the whole matrix, right? The top left entry, I and j are both equal to 1, so you get minus 1 squared, which is just 1. So that's the plus sign. And then as soon as you move over, if you move to the right, j goes to j plus 1. If you move down, I goes to I plus 1. So as soon as you move either to the right or down, that plus sign changes to a minus sign. As you keep moving either right or down, this alternates between being a positive or negative sign. So that's your cofactor. And then we have the cofactor expansion, or sometimes the plus expansion for the determinant. The determinant is then the determinant of A is, and you can write it down in two different ways. The determinant of A is a sum Aij minus 1 to the I plus j and ij, and that whole thing, if you want, you can simplify it just a tiny bit. Because that minus 1 to the I plus j mij term, you can replace with just Cij if you want. So the determinant of A is either that or determinant of A equal to the sum either of these expressions works, the determinant. And this first expression, this one over here, you're summing over j. J is the index of your columns. So this first expression corresponds to picking a row and expanding along that row. This second expression over here, I, is your row index. So this would correspond to fixing j, choosing a particular column, and then summing over all the rows in the column. So this is expanding down the column. This expands along a row, this expands down the column. Maybe that's what I was just pointing out here on the slide. So this is fixed row, and this here would be for a fixed column. So you can either fix a row and expand along the columns, or you fix a column and you expand along the rows, but you get this expression for the determinant. And you should maybe just stop and try to convince yourselves. We can just about do it. We can fit that expression up there that I've calculated for the determinant of D, and this over here, this expression here, just move up just a tiny bit so that it maybe fit, no, we can't fit B on as well. But you can see that the determinant for B, I'll be with you in a moment. It's a sum of three terms, right? So it's this sum over here we're summing. Then that +1, that -2, and that -1, that is sort of a result of this aij, the coefficient, multiplied possibly by a minus sign or a positive sign. And then those three smaller determinants, those 2 by 2 determinants, are these mij over here. So this formula here is just a more formal way of writing down what I put up earlier. So there was a question.
I'm just saying that we never defined aij.
Never defined, oh, okay, so aij is just the entry. Have I not defined it anywhere? Where's a good place to put it? We'll put it here. Matrix A is equal to matrix A11, A12, A1n, A21, AN1, ANN. So these aij are just the actual entries in your matrix. Sorry, I suppose I thought that was obvious, but maybe it isn't. Is everyone happy with this over here? Okay. So then I'm going to put up an example, and we can take a couple of minutes and try to calculate the determinant of this matrix. Calculate determinant of 1, 1, 2, 4, minus 1, 3, 0, 2, 6. And you can take, I guess, 3 minutes to do this. Yeah? A little bit, okay, sure, so that you can actually see the... Okay, so let's do this calculation. I said that the calculation is slightly easier if you choose to expand along a row or a column which contains a 0 in it. So it would make sense to expand either along the first column or along the third row. So for the sake of doing a column expansion, which we haven't seen yet, I'm going to expand down this column here. And so I just put in as a guide, this is going to be a plus, this is going to be a minus, that's going to be a plus. And now I've got to write down a sum. So this determinant 1, 1, 2, 4, minus 1, 3, 0, 2, 6, is going to be equal to. So firstly I take this 1, and I multiply it by the appropriate minor. And the minor would be, in this particular case, the minor is going to be the determinant of that matrix over there. So that'll be minus 1, 3, 2, 6. Then we've got a 4. That should be a minus 4. And we calculate the determinant of a smaller matrix. The determinant of a smaller matrix is going to be 1, 2, 2, 6. 1, 2, 2, 6. And then we get plus 0 multiplied by, and I don't even have to bother writing down the rest of that. It's going to be 0 multiplied by a minor, but we know that 0 multiplied by anything gives you 0. So this is part of the reason why we wanted to do the expansion along a row or a column which has zeros in it, because it means that part of the computation is simplified. So what we have now is, this is just 1 times by negative 6 minus 6 minus 4 times by 1 times by 6, 6 minus 4. So that will be negative 12 minus 8. That's negative 20. Okay. Is everyone happy with what we've done here? Yes.
I swapped the bottom row with the top one to get the 0 on the top.
Yeah.
I just got plus 20.
Yeah, okay, so what you've done, you're not, whenever you swap 2 rows of a matrix or 2 columns of a matrix, it changes the value of the determinant by a factor of minus 1. So this is something which we're actually, I think it's going to be a tough problem probably next week. But this is what I said a little bit earlier on in the course, or a little bit earlier on today in the lecture. I said that we can do Gauss reduction to help calculate determinants. So what we will do is we'll see that we can Gauss reduce a matrix so that it's in a sort of upper triangular form. It's very easy to calculate the determinant of an upper triangular matrix. And then we know at each step, when we do the Gauss reduction, each elementary row operation of Gauss reduction changes the value of the determinant in a well-known way. So swapping 2 rows changes the determinant by a factor of minus 1. And scaling a row by k changes the determinant by k. So that's sort of what we're going to use a little bit later on to calculate determinants. Yes, question at the back first.
If when you introduce the checkerboard pattern,
Yes.
and there's a minus on a negative entry, does that become a plus?
Yes, it becomes a plus because it's negative times by negative.
So if I swap 2 columns, will it not change the...
No, if you swap 2 columns, the determinant will also change sign. You'll get plus 20 instead of negative 20.
So then if you have to swap 2 columns and then you swap another one like that, then you get back to your original design.
Yes, so if you swap this row and that row, and then you swap this row and that row, or swap this column and this column, and if you make 2 swaps of any type, the determinant is unchanged. Okay. All right. So let's start writing up some facts about determinants. And here's the first fact. This is, I guess, a pretty obvious one. If you have a matrix which has a row or a column which is entirely zeros, right, then the determinant of that matrix is also equal to 0. And I'm not even really going to write down a proper explanation for this because the explanation is really obvious. You just calculate the determinant by expanding along that row or column of zeros. So your sum will be 0 times y minor plus 0 times y minor plus 0 times y minor plus 0 times y minor and so on. And we add up all these zeros and we still get 0.
That would also work if you don't choose the columns or the row 0.
Yes, yes. If you've got a matrix, say a 3 by 3 matrix or a 4 by 4 matrix or whatever it is, which has got a row of zeros, you know that its determinant is 0. If you then chose to calculate its determinant, for some reason, I don't know, you're a masochist, calculate its determinant by expanding along a row or a column which wasn't a row or column of zeros, you can do that calculation and you'll see that all of these terms in the sum will exactly cancel out and all sum to 0. Yeah, it doesn't matter which row or column you expand along, you'll get the same answer.
Does that squeeze, that's the whole line or what?
Okay, yes, so this is the question. I'm not sure exactly what your question is, but you're saying, is this something about how we are squeezing R3 down to a plane or a line or a point? Yeah. So what we'll see in the next couple of days is that one way of interpreting the determinant is that the determinant tells you about the volume of a unit ball after it has been transformed by that matrix. So if you have a 3 by 3 matrix, that represents a transformation from R3 into R3. And if the determinant of that matrix is equal to 0, it represents a transformation which somehow takes this unit ball and transforms it into something with 0 volume. And something with 0 volume would be something flat. It would take the unit ball and flatten it down into like a pancake or into a line or something like that. So yes, the determinant does tell us a little bit about the type of linear transformation we're interested in, but we will speak about this in more detail.
If you choose the middle row, middle column, then does your you start with negative then?
The middle row, well, I mean, what do you mean the middle row?
3 by 3.
For a 3 by 3, yeah, that'll be positive. The middle row, middle column. Oh, yeah, I mean, yeah, okay, no, it'll be negative. It'll be negative, yeah. Okay. So that was our first fact. If you have a row or column of zeros, your determinant is very easy to calculate. There are other determinants that are easy to calculate. Before we get to them, we just need to define some new types of matrix. So let A be an n by n matrix. So you've got an n by n matrix, and if the entries in this matrix, call them aij, if the entries in this matrix are equal to 0 whenever I is not the same as j, then we say that this is a diagonal matrix. And if you think about what I not equal to j means, well, this is just saying that whenever you've got entries which aren't sort of on that main diagonal, so not in the first row, first column, second row, second column, third row, third column, fourth row, fourth column, when you've got entries that are not on that main diagonal, they must be equal to 0. So then A is diagonal. And we can maybe just put in a quick example here. For example, A equal to 1, 0, 0, 0, 0, 3, 0, 0, 0, 0, 0. Okay. This would be a diagonal matrix. The diagonal matrix, because all the entries that aren't on the main diagonal are equal to 0. A diagonal matrix doesn't sort of force the entries on the main diagonal to be non-zero. It's fine that this entry over here is also equal to 0, but it says that all the entries off the main diagonal must be 0.
So,
Yes.
and is it specific that all of them are?
Yes, everything which is not on the main diagonal must be 0. So that was a diagonal matrix. If Aij is equal to 0 for I larger than j, for I strictly larger than j, then A is so if Aij, if all the entries are equal to 0 whenever the row index is bigger than the column index, then A is upper triangular. And I'll draw an example in a moment, but if you can just stop and think about what this is saying. I bigger than J says that the row, the further down you are, how far down you are is more than how far across you are. So this is really, I bigger than J is really all the entries underneath the diagonal. So if all the entries underneath the diagonal are 0, it's called upper triangular.
For example, the diagonal should A33, that shouldn't not be 0.
No. So the fact that we have a diagonal matrix, the diagonal matrix, all it says is that everything off the diagonal must be 0. It doesn't say anything about the values on the diagonal.
Okay.
And this as well, it says everything beneath the diagonal must be 0. So if we have an example here, something like this. So let's say 0, 0, 0, 0, 0, 0. But all the other entries could be, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Right? That's upper triangle. It just says that these entries over here may be 0. In fact, maybe we can make this point a little bit clearer. Take these two entries out here. This is still upper triangular. It doesn't matter that there are some entries which are 0 above the diagonal, on the diagonal. Upper triangular just says all the entries below must be equal to 0. And very similar to upper triangular, there's another type of matrix which is simply called a lower triangular matrix. And a lower triangular matrix just says all the entries above the diagonal must be 0. If Aij equal to 0 for less than j, this is just the inequality swaps around, then A is lower triangular. For example, lower triangular 1, 0, 2, 3. I'll draw a very small one. I'm tired of drawing these big ones. So that's your lower triangular matrix. All the entries above the diagonal. In this case, there's only one entry above the diagonal. It's this entry here. All the entries above the diagonal are equal to 0. You might also realize that if a matrix is a diagonal matrix, it's also an upper triangular matrix. And it's also a lower triangular matrix. And if you know that a matrix is both upper triangular and lower triangular, it must be diagonal. So are there any questions about these definitions of diagonal, lower, and upper? Yeah.
Can you explain to me what do you mean by I greater than G or I less than G?
So what I mean by I greater than J and I less than J? Well, okay, so Aij, this is, this over here tells you about your row. And this tells you about your column. Okay, so if we take a look at, let's say over here, this is I is equal to 3. Okay? And this over here would be J is equal to 1, J is equal to 2, J is equal to 3, J is equal to 4. So if we look at this entry here, I is equal to 3, J is equal to 1. So I is bigger than J, so this must be equal to 0. Then we look at this entry here, this I is equal to 3, J is equal to 2, so I is bigger than J, so this entry here must be 0. And this entry here, I and J are equal, so that we don't know anything about that. It could be any number. Yes?
So these rules don't dictate what the value of the diagonal must be?
No, they tell you that certain entries must be 0. Either the entries off the diagonal, or the entries below the diagonal, or the entries above the diagonal. They don't tell you what the other entries are. So the matrix, which has got zeros in every single entry, is a diagonal matrix, and it's an upper triangular matrix, and it's a lower triangular matrix. All right. Okay, so fact 2.2, and maybe this is something that you can think about over the weekend. Yeah, fact 2.2. So if you have a matrix A, which is a diagonal matrix, or an upper triangular matrix, or a lower triangular matrix, then the determinant of A is very easy to calculate. The determinant of A is simply the product of the diagonal entries of that matrix. Then det A is the product of the diagonal entries. You write this as det A will be A11 multiplied by A22 multiplied by A33 multiplied by A10. And you can maybe think about that over the weekend, and when we come back on Tuesday, I'll explain why this is the case. It's actually really obvious if you just think about it and you exploit the natural sort of structure of these matrices. If you've got any questions, I'll hang around now. Otherwise, I'll be in my office from 10 to 1 today with the consultation, or I'll see you next week.